Here's a problem from Thomas Calculus. This is about related rates. A 13-foot ladder is leaning against a house when its base starts to slide away. By the time the base is 12 feet from the house, the base is moving at a rate of 5 feet per second. Letter A. How fast is the top of the ladder sliding down the wall then? B. At what rate is the area of the triangle formed by the ladder, wall, and ground changing then? Letter C. At what rate is the angle theta between the ladder and the ground changing then? All three questions in this problem is asking for rate. And we know that rate is a derivative with respect to time. The first one is the rate of the distance between the ground and the top of the ladder. For letter B, it's the rate of the area, so we are looking for dA over dt. And for letter C, it's the rate of the angle theta, so we are looking for d theta over dt. According to the problem also that the base of the ladder is moving at a rate of 5 feet per second. So this number 5 is also a derivative. It's the derivative of the distance between the wall and the base of the ladder. So here's an illustration of a house, and there is a ladder leaning against its wall. The base of this ladder is sliding away from the wall of the house, and the top of this ladder is sliding down the wall of the house. I'm going to create another illustration that focuses only on the ladder, the wall, and the ground. Of course, we have to assume that the wall of the house is perpendicular to the ground. I suggest that whenever you're solving a related rate problem, you assign variables to those quantities that changes with time, but those quantities that remains the same, you can put their actual values. For example, in this case, the length of the ladder will remain the same, it's 13. But the distance between the wall and the foot of the ladder is going to change with respect to time. So I'm going to assign a variable x for that distance. Also, the distance between the ground and the top of the ladder is going to change. I will assign a variable y for that distance. According to the problem, there is an instance in time when the value of x is exactly 12, and at that precise moment, the rate of the change in x is 5 feet per second. So we can say that dx over dt is 5 feet or 5 feet per second. So question A, how fast is the top of the ladder sliding down the wall? It's asking for the rate of the y, which represents the distance between the top of the ladder and the ground. So we are looking for the value of dy over dt. We can find this value by observing that we have a right triangle where the hypotenuse is 13, the base is x, and the height is y. There is one very specific relationship that relates between the sides of a right triangle, and that is given by the Pythagorean theorem. So we can utilize the Pythagorean theorem, and we can say x squared plus y squared is equal to 13 squared. Take note that x and y are both functions of time, so we can get their derivative with respect to time. So the derivative of x squared with respect to time will be 2x times dx dt, and the derivative of y squared with respect to time is 2y times dy dt. Of course, the derivative of 13 squared is 0 because it's a constant. So this problem, how fast is the top of the ladder sliding down the wall, it's asking us to find the value of dy dt. In order for us to find the value of dy dt, we must have the values of all other quantities involved. For example, we must have the value of x, we must have the value of dx dt, and we must also have the value for y. We know that for this question it's asking for the dy dt when x is specifically 12. Also at that time the dx dt is 5. However, we don't have the value of y at this specific moment. So how are we going to find the y? We will still use our Pythagorean theorem. We will substitute x with 12, and then we are going to solve for y. So we can say that y squared is equal to 12, or rather 13 squared minus 12 squared, and that will give us 25. And solving for y, we will get positive or negative 5. We are just going to use positive 5 because y represents the distance between the top of the ladder and the ground. So now we are ready to substitute y with 5. And again, dx dt is also 5. and x is 12. So now we are going to multiply 2 times 12 times 5, and we will multiply 2 times 5. We are going to add negative 120 to the left side and the right side of this equation. And now we are going to divide the left side and the right side of this equation by 10. So we have the value for dy dt as negative 12. So therefore, we can say that at the time that the base is 5 feet from the wall, the top of the ladder is sliding down at 12 feet per second. The negative signifies the fact that the y is decreasing. Letter B. At what rate is the area of the triangle formed by the ladder, wall, and ground changing then? So we are looking for the derivative of the area with respect to time. So we are looking for the dA over dt. To find this, we will use the derivative, or rather the formula for area of a triangle, which is 1/2 of the base times the height. So in this case, we are going to say 1/2 of x times y. I'm going to separate 1/2 x as my first function and y as the second function. I'm doing this because now I'm going to get the derivative of the left side and the right side with respect to time. And since there are two functions involved at the right side, I'm going to use the product rule. So the derivative of a with respect to time is dA over dt. That's for the left side. And I'm going to apply the product rule for the right side. So I have dA over dt times, or rather equals to the first function, 1/2 x, times the derivative of the second function, that is dy over dt, plus the second function y times the derivative of 1/2 x, which is 1/2 times dx dt. So we have to substitute all values involved. For example, the x will be 12, the dy dt is negative 12, the y is 5, and the dx dt is also 5. So substituting all these values, we have dA over dt is equals to 1/2 times 12 times negative 12 plus 5 times 1/2 times 5. So multiplying that, and we get negative 72 plus 25 over 2. If you're going to solve this expression, eventually you're going to get negative 119 over 2. So this is the rate of the change in the area, so the unit must be square feet per second. So question C. At what rate is the angle theta between the ladder and the ground changing then? So we have here the angle theta. It's located between the ground and the hypotenuse, which represents the ladder. We're looking for the rate of this angle, so we're looking for d theta over dt. If you carefully observe our triangle, you can see that the quantity opposite to the angle theta is y, the adjacent is x, and the hypotenuse is 13. So we can use the sine function. We can say that the sine of the angle theta is equals to y over 13. We can use this, get the derivative of the left side and the right side with respect to time, and we will be able to get the answer or the value for d theta over dt. The derivative of sine theta is cosine theta times d theta over dt, and the derivative of y over 13 on the right side is 1 over 13 times dy over dt. We have to find the value of d theta over dt, so we must have the value for cosine theta as well as dy over dt. We already have the value for dy dt. We know it to be negative 12. However, we still don't have the value for cosine theta. But we have the value specifically for x, which is 12, and the value for y when x is 12 is 5. We also have, of course, the dx over dt as 5 and the dy over dt as negative 12. If we are going to substitute now x with 12 and y with 5, so we have now a triangle, a right triangle with hypotenuse 13. The vertical side is 5 and the horizontal side is 12. So now we are going to apply the cosine function, and cosine is defined to be in a right triangle as the side adjacent to the angle theta and divided by the hypotenuse. In this case, it's 13. So therefore, the value for cosine theta is actually 12 over 13. So now we are ready to substitute these values into our equation. So we now have cosine theta will be replaced by 12 over 13 multiplied by d theta over dt, and the dy over dt is substituted with negative 12. I multiplied left and right, left side and right side of this equation by 13. So I have 12 d theta over dt equals to negative 12. Now we can divide by 12 left side and right side of this equation. So we have d theta over dt equals to negative 1. So this is the rate of the angle theta with respect to time.